Okay, good. Yeah, I'm here. Should I go ahead and start?
Yep. Yes.
Thanks for having me. I wanted to provide some context for the overall field. This is work in collaboration with Matt Fitzgerald in Audiology at Stanford, and work I've been doing with over many years with Dick Lyon at Google, and certainly a bunch of other people, local and around the world. As Jan, I can change slides. As Jan mentioned, what I want to talk about today is largely based on a special session we had at ARO in February I forget where we were. And I had some wonderful speakers talking about different aspects of deep neural networks and AI for auditory modeling. And so a lot of the work that I'm presenting today is based on what they've done and others and some of my work. But I do want to give credit to these six who contributed a lot to the ARO session and I think represent a wide cross-section of work that's out there. So with that, this is not the focus of my talk, but I want to mention it because everybody thinks about large language models in in the modern world. And this particular image is up here because it's an illustration of a stochastic parrot, which is what people normally think about, or how people characterize large language models. And so the idea is that if you ask a large language model a question or give it some text, it'll just continue rambling on forever. And it has these very detailed models of what text sounds like. And so I can ask, what is tinnitus? And LLM say, tinnitus, the perception of a ringing, buzzing sound, blah, 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 blah. And it'll go on forever. But it doesn't really have any understanding of semantics. It just knows that if you say the word, the Gettysburg address is going to be the next word. So for people in the US, the Gettysburg Address is just sort of a given. And so that's the level that they know, but they actually know a lot about language, and people have written a lot of things. And so if you ask something like, what is tinnitus? There's a whole bunch of text that it can mine on the internet and books that give a pretty reasonable answer for what tinnitus is. And where they fail is to say, well, what time does the Stanford Ear Clinic open on Labor Day? And these models don't have that kind of detail unless they have a way of talking to an external database. Again, this is not the focus of my talk, but it's out there, and I want to distinguish what we're doing from that. So all of you know this, but I wanted to put some context in what we're doing. A lot of audiology is based on audibility and fixing thresholds and amplifying, compressing. And a large part of what we're doing going forward is how do you deal with these higher level aspects of hearing, like the hidden hearing loss, like synaptopathy and cognition. And these are all important issues as we move beyond audibility and as we start thinking about other aspects of auditory health. And a lot of these AI techniques are addressing these kind of conditions. So if you take nothing more from this talk, this is the main slide. You can ask lots of questions and we can skip the rest of the slides if you want. But largely, the models that are being done today are either descriptive, saying, okay, this is a model that describes the behavior we're seeing. So we've measured performance on some auditory task, and we build a model of that. That's sort of fundamental to every psychoacoustiциan's thesis is some sort of descriptive model. And what's more interesting, more challenging is building functional models, so models that actually explain the details of what's going on with more or less biological plausibility. And I think the really interesting stuff is these functional models, because then we can use them to do new things, not just describe the data. So Josh McDermott has been working on descriptive models for a long time, 10 or 20 years probably. And he asked the question is, can we build better models using machine learning? And I think the question then is, what is a better model? And he has his definition. They hardwire the cochlea to the biology. So he's in his approach. I think Fotios is going to talk about a different approach, but in Josh's approach, he says we know what a cochlea looks like. We know how to model it. We have very detailed models of the biomechanics. We'll just use that, and then everything else he does is on top of a hardwired cochlear model, which is fine. And everything else is just modeled with neural networks, as shown in this figure. So what he takes away from all this is that he can build task optimized models that tend to converge to human-like behavior. And so he's used these models to explain classical psychoacoustics results like pitch and spatial hearing, which is a great first start. But the more interesting stuff is, can he explain higher level cognitive signals like speech and environmental sounds? And so these two figures are from one of his recent papers showing on the left speech recognition performance versus one of his models. So this is human versus machine. And then the same sort of thing for speaker recognition. He calls it voice recognition, but speaker recognition. So can you tell who is speaking? In this case, people are much better than the models. It is what it is. And then I've been looking at, can we use these models to actually model human performance on a speech and noise test like SquickSyn. So what you're seeing in the bottom figure is speech reception or speech comprehension on a speech and noise test between 0 and 25 dB, showing that different models, these are all state-of-the-art foundation speech recognition models, perform more or less well. And the best models are achieving a speech reception threshold of 3 dB, which is, at the high end of normal. So they're not normal yet, but they're certainly approaching that level. And so I think that's quite impressive that these models can do that. For a long time, these models of speech recognition has performed better than humans at clean speech, and they're still not there for noisy speech. And I think the interesting question is are humans and machines operating at the limit of information? So there's only so much information in a noisy speech signal, and humans are optimized to get that out. I mean, we've evolved for millions of years to optimize speech recognition in noisy environments, and arguably we're doing as well as we can given the information that's there, given the waveform. And our speech recognition systems getting to the same level, or will they actually exceed it? We don't know yet. So that's this descriptive models. And what I want to talk next is a flavor of models in a framework for doing enhancement. So not only are they trying to explain the auditory system in a biologically plausible way, biophysically plausible, but they actually want to put it in a loop. And I like using this diagram to illustrate what we're trying to do. So what's shown here so far is just an audio signal going into a normal auditory system. This is what we're all playing with now, or most of us are playing with now. Normal is normal. But what we really want to do is want to start modeling the abnormal auditory system. And the way I describe this to my corporate benefactors is anybody over the age of 18 has less than perfect hearing. So we want to generate models for everybody over the age of 18 because all of us have less than perfect hearing. And we do that by, as you can see in this figure, we match the model. We tweak the model, we optimize the model so that the model explains your psychophysics. So if you give us a tone and noise or a masking experiment or a modulation experiment, or even a speech recognition experiment, we want to tweak the model, tweak our auditory model, whatever it is, to give exactly the same performance you do. So this is an individualized model of your hearing, not the generic ones that we were all used to. So that's the first step. We call that the hyper-personalized model. And then the real key is we want to put an enhancer in front of that. So we want to build an enhancer. Today, that's just a hearing aid. It's just an amplifier. What we really want to do is build a full enhancer that does everything. Amplification, compression, helps sharpen things if necessary, reduces the noise, whatever it can do, so that if you put it in front of this abnormal auditory system, what comes out is something that closely matches a normal auditory system. And then so what we have to do is this blue line at the bottom, we want to optimize the enhancer. So we've frozen the model of the auditory system. We want to optimize the enhancer so we get the best possible signal. And either that's matching the signal or optimizing it, improving it. And we can do several kinds of tasks like speech recognition, modulation, detection, masking. So in the ideal world, what we really want to do is we want to optimize our model so that human speech recognition is as good as possible. And then we want to do the same thing for music. And this is a general model, and all the work that follows this presentation is of that flavor. How do you apply this model to those kind of things? So Sarah Volholst at Ghent has been working on this for a while, and her particular model looks like this. She builds a biophysically analytic model of the auditory processing system of the auditory, especially the cochlea, the inner hair cell, and the auditory nerve fibers. And that's shown in these different models. And the key idea in this is that they have very detailed models of all these three stages. So they know what a cochlea does, they know what a hair cell does, they know how the auditory nerve firing happens, and they can build models for all things. And then they can train each one of these things separately. So this is showing their pipeline with the cochlea, the inner hair cell, and the auditory nerve fiber. And I suspect Photios will go into more detail. But they do these individually. And this is contrary. I mean, this is a good way to make progress, but it's worth noting this is contrary to current deep learning DNN techniques, which build a single optimization layer to optimize everything. So everybody gets the best performance if you do an end-to-end optimizer. And we're not at that level yet. We're not able to do that kind of thing because we don't have enough details to make it all work. And because also we're trying to do a model that's faithful to the cochlea, faithful to the hair cells, faithful to the inner hair cells. So again, this is the tension between explainability and performance. And this is tending toward the explainability point of view. Separate approach is what Marianne Hosseini and her colleagues at Macquarie and Cochlear are doing in terms of doing exactly the same optimization loop that I just showed you. But now they're doing it for cochlear implant users. So now we have a user that has a very severely impaired auditory system. We have a very primitive approach to driving it with electrical stimulation along the cochlea. And it's exactly the same figure I showed you before, except now this block here is outputting electrical signals to the cochlea. And where it becomes interesting is that this model can be optimized using a model of a voltage spread or current spread in the cochlea. And so what you want to do is, given this person's electrode placement, given the model you have of their current spread, you can then build an enhancer that then drives the optimal set of pulses to drive this cochlea. And it's exactly the same thing. And she reported on her progress on this effect at ARO, and they have some papers out. So again, it's the same process, and you can do the same thing. A third approach was proposed by Anil at Ruhr in Germany, using a WaveNet, which is another way of building these networks, and not layer by layer like I showed in the previous thing, but you have these convolutional layers that build on top of each other. Originally, this was done for speech synthesis, but he's using it for modeling the auditory system. And the unique thing about what he's doing is shown in this circle here, where he's conditioning the model, that's the terminology people use, based on your individual audiogram. So instead of trying to optimize a model for a user, he's trying to build a model that can model any auditory system, and you just tell it what the audiogram looks like. So you feed an audiogram, and this model has already been trained to deal with all the possible auditory systems and all the different auditory audiograms, and so it can quickly generate a result for that user. So it's a generic impaired model is what I called it. One of the issues with all these things is that, and I actually don't remember whose figure this was, because I don't want to blame any one group, but everybody gets good performance. I mean, they build a model, they give it training data, the loss goes down, and if it didn't go down, they wouldn't report it. But so all the results show the results going down, but you don't necessarily get something that makes sense. And so this is showing one particular result where they do a good job at modeling the peak. And so you see this nice peak that matches between the transmission line, the physical model, and the neural network model. But then, there's this issue down in the tails where you don't get good results. And I think this is one of the things that's hard about auditory modeling, is that people who do computer vision only care about 8 bits or 16 bits of precision. You get 8-bit image in, you work with it, everything works fine. You can do a ReLU. you don't have to deal with things like compression and stuff. And so I think one of the things that we have to address is how do you handle the large dynamic range that's inherent in the auditory system? So this, this particular graph is showing 80 dB dynamic range, which is way more than any visual system ever has to deal with. And it's hard to get the right metric. But at least something to think about. Finally, there's been a lot of work lately on building these foundation models. And so all the recent generative work, all the stuff that's going on now is how do you train models with millions of hours of data to learn something about speech signals, for example, or text. So this is Whisper's model. The left-hand side is a training loop where you give it some spectrograms and you have this architecture that tries to predict spectrograms. So you give it a spectrogram with holes in it, and the network has to learn the information that's missing. And so by doing this, it learns a lot about what speech sounds like. And in this case, you're applying it to a set of transformers, decoders, that try to do speech recognition. This works really well, and you get these massively good results. So, and again, this is with millions of hours of training data, more than we can ever get from one person, but they work really well. They know a lot about speech. And these different layers have different amounts of semantic information. So as you go from the low level to the high level, they have more information about meaning and emotion and things like that, the higher level cognitive effects that we really want to be able to help people with. We don't want people make the speech just audible. We want to make sure they understand the words and also to understand the meaning. And so these semantic levels get at that information. And so he builds a similar kind of model where the green things, he's inserted a foundation model. And so now the idea is, can you build a model that matches the semantic information from an abnormal auditory system and a normal auditory system so that the user gets the same message? So with that, just in summary, these things work because they're differentiable and have large amounts of data. Differentiable is important because you need to be able to take your output and say, okay, I made a mistake. How do I tweak my model to get the right answer? And that's done by differentiating the model and saying, okay, the error here gets translated into a change in the parameter here, which is also changing a parameter here. And so we can do that, and we know how to do that with large amounts of CPU power, and it works really well. That's why DNNs and AI is so impressive these days. But there still remains a lot of issues. So do you want to have separate models because they're more explainable or unified? Do you want to have biologically realistic or black box models? And I guess the really important question is, what's your error measure? Do you want to measure just accuracy of the waveform? Do you want to measure accuracy of the hair cell model? Or do you want to measure accuracy of the speech recognition and listening effort? So you guys are all listening to me in a relatively clean environment. Listening effort is hopefully very low for you because I'm speaking fast, but not in a weird accent. How can we give that experience to people with abnormal hearing? And that's what I wanted to talk about today. And hopefully that's a good introduction to Photios' talk. Thanks, everybody.